Hello, my name is Thomas Diem, and I'm going to be talking about Section 4.9, Antiderivatives. In this video, I will go over what an antiderivative is, and how to find the antiderivative of certain functions. I will go over the power rule for antiderivatives, and the antiderivatives of logarithmic, exponential, and trigonometric functions. Taking the antiderivative is an operation that reverses what a derivative does. When you take the derivative of a polynomial, you subtract 1 from the exponent, and multiply by the old exponent. Since the derivative is the opposite of the antiderivative, you find the antiderivative by adding 1 to the exponent and dividing by the new exponent. So the antiderivative of a single term expression, x to the n, can be written as x to the n plus 1 divided by n plus 1. To take the antiderivative of a polynomial, you can just do this process with each term. For example, if we want to take the antiderivative of the function f of x equals x to the fifth plus 4x cubed plus 2x squared plus x, we can use this process. For each term, we add 1 to the exponent and divide the term by the new exponent. We can then simplify the answer, and we can simplify more by canceling out the 4's in the second term. We get the solution of x to the 6th over 6 plus x to the 4th plus 2x cubed over 3 plus x squared over 2. If we want to check our work, we can take the derivative of the new function we found, and it should be equal to the original function. If we take the derivative of our answer, we will indeed get the original function. However, this is not the final answer. Remember that when we take the derivative of a function, the derivative of any constant is 0. So in theory, there could be any constant at the end of the function, and it would still be an antiderivative. For example, if we write our function as x cubed over 6 plus x to the 4th plus 2x cubed over 3 plus x squared over 2 plus 10, and take the derivative of that, we would still receive our original function. Since this would work for any constant, we would write our final answer as x to the 6th over 6 plus x to the 4th plus 2x cubed over 3 plus x squared over 2 plus c, where c represents any constant. A common mistake that students make is that they forget to write plus c at the end of the expression. This graph shows f of x as the red line and its antiderivative as the blue line. We can see that the y value in the red line is the same as the instantaneous slope in the blue line. In this particular graph, the c value of the antiderivative is 0, but it would still work if there were a different c value. For example, in this graph, the c value is negative 3, but we can see that the y value in the red line still describes the instantaneous slope in the blue line. This is because the constant at the end of the expression doesn't affect the slope of the line. Let's do a harder example. To find the antiderivative of a function such as f of x equals 10 over x to the 9th plus root x, we can use the same rules that we used in the first example. It would be easier to solve this problem if we rewrote the exponents in this equation. We get the integral of 10x to the negative 9th plus x to the 1/2 dx. It is also another common mistake to forget to write dx or d of whatever variable you are using at the end of the integral. Although this may not seem important, it has significance in later chapters of the book. Now that we have rewritten the exponents, we can find the antiderivative. Again, we add 1 to each exponent and divide by the new exponent. We get 10x to the negative 8th over negative 8 plus x to the 3/2 over 3/2 plus c. After some simplification, our final answer is negative 5 over 4x to the 8th plus 2x to the 3/2 over 3 plus c. Now that we know the power rule for antiderivatives, we need to know how to find the antiderivatives of other functions. Let's start with logarithmic and exponential functions. There are two identities that we need to know for these functions. They are both very familiar from previous chapters. The first is that the antiderivative of e to the x is e to the x plus c. This makes sense because we have already learned that the derivative of e to the x is e to the x, so we can work backwards to find this identity. Another identity that we need to know is that the antiderivative of 1 over x is ln of the absolute value of x plus c. This should make sense based on what we've learned doing derivatives. Another common mistake is that students forget to write their absolute value sign, which is necessary because the ln of a negative number does not exist. This section also covers identities of 9 trigonometric functions, all of which should be familiar from previous chapters. The antiderivative of sine x is negative cosine x plus c. The antiderivative of cosine x is sine x plus c. The antiderivative of secant squared x is tangent x plus c. The antiderivative of secant x tangent x is secant x plus c. The antiderivative of cosecant squared x is negative cotangent x plus c. The antiderivative of cosecant x cotangent x is negative cosecant x plus c. There are also identities we need to know for inverse trig functions. The antiderivative of 1 over root 1 minus x squared is sine inverse of x plus c. The antiderivative of 1 over 1 plus x squared is tangent inverse plus c. The antiderivative of 1 over x times root x squared minus 1 is secant inverse x plus c. Let's do some sample problems with this information. Find the antiderivative of the function f of x equals 3 e to the x minus 5 over x plus 3 cosine x plus secant x tangent x. We can solve this integral by finding the antiderivative of each term separately. We can put each constant outside of the integral. Although these steps might be unnecessary, they show us the rules of taking antiderivatives. Using the identities given earlier in the video, we can solve for the antiderivative. Some questions in this section will ask you to find f of x with given information. One question could be, find f of x given that f double prime of x equals sine x minus cosine x, and that f prime of 0 equals 4, and f of 0 equals 3. Our first step would be to find f prime of x by taking the antiderivative of f double prime of x. Using the identities that we learned earlier, f prime of x equals negative cosine of x plus sine of x plus c. We can use the given information that f prime of 0 equals 4 to find c in this equation. We plug in 4 for f prime of x and 0 for x. We can simplify this, and we get c equals 5. So now that we know that f prime of x equals negative cosine x plus sine x plus 5, our next step is to find f of x by taking the antiderivative of f prime of x. We get f of x equals negative sine x minus cosine x plus 5x plus d, which is a variable we use to not get confused with the other variable c. We know that f of 0 equals 3, so we can substitute these values. We can simplify more, and we get d equals 4, which then we can substitute back into the equation. Our final answer is f of x equals negative sine of x minus cosine of x plus 5x plus 4. Let's do a problem that requires more thinking than the previous ones. We want to find the antiderivative of x squared over x squared plus 1. It should be noted that this is not equal to x squared over x squared plus x squared over 1. However, if we think back to earlier in this video, we might remember that the antiderivative of 1 over x squared plus 1 is equal to the inverse tangent of x. If you want to attempt this problem on your own, pause the video and try to separate the numerator and apply this information. We can solve this problem by rewriting the numerator as x squared plus 1 minus 1. Now we can break this into two fractions. We can simplify the expression and take the integral. We get a final answer of x minus tangent inverse of x plus c.